Okay, so if you recall, in the previous lecture, we were talking about the first category of caches, right? We call them direct cache or direct map cache because we are actually mapping directly one-on-one the address to the cache, but we just use a mod function or modulo in order to find the specific location of that, and it's a log base of the number of addresses that are coming. Okay, so we had an example here. I thought let's have another review on that. So we have, using the tag bits depending on the size of the address and the memory addressing. So we have a tag segment, we have a data segment, we have another bit called validity bit. So either we have to set it to 1 or not. So 0 shown here by n and 1 shown here by y, right? And we have one index as well. So the index actually shows you what block of cache you are accessing, right? So the initial state would be all none. Say you just restarted or flushed your cache, so nothing is there. So the first one comes, the first address, right? So the first one is telling us a cache block to look up at number 110. So 110 in an 8 So the actual binary address is 5, and I mentioned that in this specific example, because we have only 2 bits of tag, the rest of the 3 are actually showing you the cache block, okay, from 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have, with 3 bits, we can represent 8 of those, right, using index. So using this, we're gonna find that, okay, we have to look up 110, which is this log, and we see the tag 10. Since nothing was there, automatically it's gonna be a miss. So at this point, we need to set this n to y because that was a miss. So we have to go down to the lower level of cache hierarchy. If it was L1, we're going to go to L2. If it was L2, if we had L3, we're going to go to L3. If not, we're going to go to memory, right? So one level lower in the hierarchy of the memory. So L1, L2, L3 if there was, or mem. Okay, you go one level lower, you find the data. If not, you have to go one level even lower. Say we found it, we only had L1 and mem, right? So after this, we have to go to memory and look it up. We bring back the data that we were looking for. So the mem of 10110, and then the tag is going to be placed here. We set the validity bit from 0 to 1, so it's going to be y here, and then that's going to be a miss, right? So that was the first instance. So the next instance, we talked about this in the example. The next one is 11010. So again, we look at the last 3 least significant bits. 010, it shows this block using this index, right? Nothing was there, and the validity was 0. We set it to 1 again. We come back to the lower level. We fetch the data. It's going to be the mem of 11010, and then that's going to be another miss. Okay. Next one again. We have to look up in this address 110, right? And 110 was already been set by the 2 misses ago, and then we found that the tag is also the same, so that's going to be a hit. So we are reusing some data that was brought up from the lower level, okay? And that's the reason we use caches, because we want to keep something closer to us that we keep using, right? We put something closer to us. If not, you have to just come down and find it elsewhere. So it was there already, so that's going to be a hit. And then we move on. The next time, so we're going to have a miss on this line, 3 triple zeros and 10 for the tag. So it was a miss. We brought it up again from the mem. And the last one here, we have another miss. Although some data used to be here, but the tag didn't match because the previous tag was 11, you see, but the tag we were looking for had 10. It was another data. So it considered another miss for itself. Okay, so that was pretty much an intuitive way to find cache misses versus hits in a direct map cache. Okay, there are 3 more versions or 2 more versions at least that we're gonna learn next lecture. Okay, all right. Let's see another example about caches. So how are we gonna divide or subdivide the addresses? So as far as we've understood so far, we have something like this in order to address. So one portion of the data or the address is going to be for offset. One portion is for tag, and one is for index. Okay. Normally, because it's a direct map, depending on the length of this, the size of the cache. For instance, for this cache, we have from 0 to 1023, right? 1024 lines of cache. Okay, so I could represent this with how many bits? So I have to represent a direct map cache of a length of 1024, right? How many bits I need to? 8. 2 to the 8, to the raise of 8, what's gonna happen?
256.
So is it enough?
2 to the 10.
Yep. 2 to the 10 is gonna be 1024. Okay, so I need 10 bits in my index to be able to find the lines. Okay, it's gonna be 1024. All right. Then that's why you have from 2, right, to 11. So that's the index here. So this cache holds 1024 words, right? We saw it here, or 4 kilobytes, right? So 4 words per line. So you're gonna have a log of that. It's gonna be 2. Log of 4 is gonna be 2. So that's why you need 2 bits for offset. The 4. So you add these two together. 10 plus 2 is gonna be 12, right? The addressing was 64. The memory addressing overall. And then whatever remains is going to be for your tag, right? So 64 minus 10 minus 2, okay? Yep.
Could you explain what address this is for? It says address subdivision. It's the address of what?
So it's those instructions that you want to execute, yeah, right? So first you have to check your highest hierarchy in memory, which is your first cache, L1 cache, right? You're looking into fetching some data that are corresponding to this address, okay? If you found it at L1, good for you. It's a miss, right? It's a hit, okay? If you didn't find it, you have to just go down through the hierarchy, okay? Just like the example we saw here. We are looking into finding these addresses. So this is 16. It's going to be translated to 10, 4 and 4 zeros, right? 3 is going to be 00011. Okay. Any questions so far? Okay, so we figured that we need 10 bits here for index, 2 bits for offset. That's why it has from 0 and 1, so 2 bits here. From 2 to 11 is 10 bits for index, and the rest is for tag. Right? You see 52 for tags, 10 for index. And then the way we subdivide this, right? And these are the data, okay? So normally if the tag and the upper 52 bits, right, if the tag of the address are equal and the valid bit is on, right, then the request is actually translates as hit. Otherwise, if either of those, the tag didn't match or the upper 52 didn't match, so we're gonna have a miss. Okay, so that's the way we do that in general. That's a very, very high level. There are so many other tweaks that we need to take care. We're gonna learn some of them today, some of them next week. Okay. All right. So what if we have larger block size, right? We can have any block size depending on the architecture of the memory or the memory hierarchy. Okay. For instance, here, what if we have 64 blocks? Okay, and each of those are gonna get considered as 16 blocks, 16 bytes per block, right? So easily you can understand that when you have 64 blocks and the block size is 16 bytes per block, so to what block number does address 1200 map? You just have to divide this, the address to the number of bytes per block, okay, and that's going to be the block address, because each of those were 16 bytes per block, okay, and a block number is a simple mod of 75 by 64, right? I'm sure all of you know what mod is, right? It's going to get you the remainder, right? So the remainder of 64 out of 75 is 11. So that's why you understand that you have to place it where exactly in a direct map cache. So given this, now you're going to find that you have 4 bits for offset, 6 bits for index from 4 to 9, and the rest are for tags. Okay. Now let's see the trade-off between having a larger block or a smaller block. In general, having a larger block should reduce miss rate because we are taking into account the using larger spatial locality. If you recall, in the last lecture I was talking about 2 different principles of locality. Let me just quickly show them here. So we had one as temporal locality. The items that are recently accessed are going to get likely to get accessed again, right? So you're in a loop, you're accessing some iterator or some parameter, so you might want to access it again in a loop. And we had another concept which was called spatial locality, and it was basically mentioning that the items that have been accessed, you want to access their nearbys or the contiguous items more likely, perhaps in a loop or elsewhere, right? And I was talking about these nested loops, and I mentioned that the temporal ones are those that are referenced to A of I because A has been used 20 times and 10 times in total, right? And J and I because every time we are using a value, right? So those references to these 3 are going to get considered a temporal locality. And for a spatial, because for the array of A, we are iterating over that, right? So A plus I plus 5, and then I plus 6, and so on and so forth. So we are continuing, we carry on using the contiguous memory locations, right? So this is considered some references as spatial locality. So having a larger block size right should technically reduce miss rates because we are using more spatial locality, right? We can fit more stuff next to each other. But in a fixed size cache, on the other side, paying the trade-off, larger blocks, we're going to have fear of them, of course, because we are dividing our chunk into larger chunks, right? So there's going to be more competition, and thus we're going to have an increased miss rate, right? There's one term sometimes it is used for that, and it is called pollution, right? Larger blocks, we're gonna have more pollution. All right. So let's see what's happening when we have a cache miss. So we understood that when we wanted to find something and it wasn't there in the highest level of memory hierarchy, so we consider it a miss. We need to come down and find that data from a lower level, say from memory, and bring that back up. Okay. So let's see what exactly is a miss. So on cache hit, CPU proceeds normally because we were looking for something right away, we found it, so it was a hit. But on a case of a miss, so which was a request for data, right, from the cache that could not be filled because the data was not present in a cache, right? So the flow of steps needs to be done are simply, first of all, we need to send the original PC value to the memory. We need to keep that because we're going to have some sort of stalls here. Then we're going to instruct main memory to perform a read and wait for memory to complete its accesses, right? Then we have to write the cache entry. You have to find that and then write the cache entry, putting the data from memory in data portion. Say we found it from memory, right? And then finally, we're going to restart the instruction execution at the first step, okay? All right. So there are multiple ways we can implement a cache when we want to write something on it. The first notion is write true. So write true is going to get considered sort of a scheme to write on caches, a scheme in which we update both the cache and the next lower level memory at the same time, no matter what, right? So say in memory hierarchy we have L1 cache and memory. Every time we want to write, we both write on the cache and also at memory hierarchy. So we want to make these two updated together to keep track of everything, and both instances, both copies should be updated at the same time. So this scheme is called write true. Okay, we ensure that data are always consistent between the two, locations. Say we had like 3 levels of cache and 1 memory, so this could have been done at 4 instances at the same time. Okay, in order to do so, sometimes it is costly because I have to spend more energy and more effort to update 2 or multiple locations at the same time. For instance, if the base CPI, right, was 1 and only 10% of the instructions were stored and write to memory to 100 cycles, right, the effective CPI out of this concept is going to be 1, which was the old one, plus 10% of the time that we pay the price of 100 cycles, right? So you see that the effective CPI is way, way higher than what the base CPI should be because we are writing all the time. So one solution to overcome this limitation is to use a write buffer. So it's going to act as sort of a queue for you, a queue that holds data while the data are waiting to be written to memory, right? So it just holds the data, and then CPU continues immediately. So you don't have to wait for that because it's going to affect your CPI every time you have to wait, right? Is it clear?
Could you go over the CPI and why it increases to 11 again?
So because we are using, on all data writes, on all data write heat, we are just updating the whole block in cache, but we are doing a redundant update in memory as well to make sure that the data that was updated is consistent with memory, or whatever, how many level of memory hierarchy we had, right? So for each of those stores, right, which involves another write, we need to do this redundant job again. So although technically the base CPI was 1 and 10% of the instructions were right, but if you add them all, so you're going to have 10% multiply 100 cycle that we have to pay the price for this to write to memory, plus the original base. So it's going to affect it a lot, right? That's why we use for this solution, we can use a write buffer in order to overcome that.
Why does write to memory take 100 cycles?
Because memory is way slower than cache, right? It's further away, you need some time to transfer to the data.
Does it always take 100 cycles?
No, in this case. So you recall in a previous last session we were talking about differences in speed, right? Mm-hmm. So SRAM was the highest, your cache. So it's around less than a nanosecond up to around 2 nanoseconds. So these information are for 2012. Now they are even faster. I believe this is for DDR3. So we have DDR4, and in a few months we're going to have DDR5 released. And DRAM is your memory. You see what's the ratio here? At least 20 to 30 times slower. But it gives us a very larger chunk of space to just store stuff, right? And it is cheaper. So this is a trade-off.
And what if the buffer is full?
So the buffer is used as a queue so that every time you want to write, you don't have to wait for that, right? The CPU can carry on working, and then that buffer gradually writes and updates the CPU, and updates the memory, right? Was that clear? So say you want to write, I don't know, 12, 25, 29, 01, right? Instead of waiting and then going back, waiting here, going back, waiting here, going back, waiting here, you carry on working, executing your processor, right? And then this one gradually updates in a queue, one after another, right? So this write buffer just does the job in a queue-based operation. Okay, so that was the first scheme, write through. The next one is called write back. It's an alternative to write through. So on only data write hits, we update the block cache. However, we keep track of whether each block is dirty or not. So it is a scheme that handles write by updating values only to the block in cache, then writing the modified block to the lower level, not all of those writes, right? So that's why there is this term that they use as dirty. So when a dirty block is replaced, it's going to only write it back to memory. If it wasn't, we don't have to write. Okay. So on this specific case, also we can use a write buffer to allow replacing block to be read first. So either of these two can be used in order to keep the data consistent with each other. Okay, so in general, what should happen on write misses, right? So there are alternative for write through, as I mentioned. So we can allocate it only on misses, and sometimes we don't need to fetch the block, since the program often write a whole block, right, before reading. And for write back, normally we have to fetch the block for that matter. So let's have an example on a real world machine that was using actually a version of RISC, right? RISC CPU. It was called Intrinsity FastMATH. So it was a company that was producing this LE 2000. So it has a 12-stage pipeline, and so normally for performance issues, for performance related matters, sometimes we use two different caches, one as I cache or instruction cache, and one as D cache, as a data cache. So we can split one cache into two, and so each of them just do one job, only indexing for instructions, or just handle the data, okay? So that these two can be parallelized. So for performance purposes, sometimes we split caches into I and D. Okay, normally in real world machines, we have I cache or D cache. So for instance, in this case, in this machine, for the FastMATH of Intrinsity, we had 16 kilobytes, right, each of them, and the blocks were 256 and 16 words per block. So if you multiply this, you're going to see the overall number of blocks. For D cache, it was using either of those, so a write through or write back. And this is one of the benchmarks that we talked about in the first chapter. So it's a standard benchmark. Sometimes you want to benchmark your performance, so it's Spec 2000, right? On that benchmark, the miss rates for I cache was less than 0.5%, and for D cache, it was around 11%, right? So we get average of these two. It's gonna be this number. Okay, so that was the overall high-level view of the cache that was using Intrinsity FastMATH. So here in this specific machine, we were using 32 bits addressing. These were for offset. Okay, so this was for block offset, the 4, the 8, and 18 we were using for tag. And here, because we are using two different a split version of caches, so we need a multiplexer here in order to handle that. So the tag field is 18-bit wide and the index field is 8-bit. Okay, this is the index. This is tag. While a 4-bit field, which is from 2 to 5, is used to index the block and select the word from the block using a 16:1 multiplexer, right? So that was used for block indexing. Okay. Sometimes in practice, instead of using that multiplexer to choose, sometimes we use a larger RAM for the tags, okay, in order to avoid that multiplexer. Because again, we have to spend some time so that the multiplexer outputs what do we have to fetch from data, right? So this will have its own penalty as well. So in order to avoid that, sometimes they use a separate RAM for that, for a larger data. So we don't need to choose from these 32s to come up with another 32, right? If we had a larger size, we could have directly find the output of this. Okay. So that's just an example of a real-world machine that was using sort of a very simplified 32-bit addressing of cache. Okay. So let's talk about measuring cache performance. So just like what we had in the first chapter, so now we are adding another element to our performance evaluation. So in order to incorporate that, we need to compute the cache hit times as well to the equation. Okay. So after simplifying that, so we're going to have memory accesses per program multiply miss rate multiply miss penalty. So we can expand this memory accesses per program to instructions per program multiply misses per instruction, and multiply miss penalty, okay? So now we need to take into account the misses and the rate of the misses, okay? So for instance, the question could be, you have an I-cache miss rate of 2, right? A D-cache miss rate of 4, and a miss penalty of 100 cycles whenever you have a miss. So the base CPI is 2, and load and stores are taking 36% of the instructions. So by this load and store, you're going to understand that this is the amount of time you might have a miss, because on load and store, you get a miss. Okay? So determine how much faster a processor would run with a perfect cache that never missed. Okay? So how are we going to find the answer for this? Any ideas?
Find the total percentage of instructions where it will miss, multiply by 100 cycles, and that's the number that we totally miss in total.
Mm-hmm.
So that's that number that we miss is the total amount of cycles that is so a lot of cycles more that it takes an ideal processor to work.
Okay, yeah. Right. So, as your colleague mentioned, so per instruction, we have to find the number of misses, right? It was 2% and 4%. I cache 2%, D cache 4%. So 2%, 400. So it's going to be 2. And 4%, here it was 36, right? So it's going to be 144 and 2. So this is per instruction. If you wanted to represent it overall, you would have just used 2 multiply I, or 144 multiply I by the number of instructions. But per instruction is going to be 2 and 144, right? So you make an average, 2 and 144 is going to be 344 on average per instruction, right? And then you use that CPU time with stall and CPU time with perfect cache, which we are looking for. So I's are going to get resolved by itself. So CPU with the stall multiply clock rate, clock cycle, and divided by the perfect CPI and its clock cycle. So you divide these two together, and then you're going to have 272. Okay? Was that clear? So this could be an easy example you might see in exam.
Sorry, one more time. What's the difference between I-cache and D-cache?
So in order to speed up the performance of a cache, we can split caches, right? Because a cache has the looking for data, like here's, for instance, let me just bring it to you. Not sure where my example was. Forgot where it was. Yeah, for instance here. So in order to, for performance reasons, we might have one I cache and one D cache. So we're going to separate our cache for D and I. So it makes it possible to fetch instructions and data in parallel. So we have to deal with the data using data cache and instructions using I cache. Okay, and normally we take the average of both of them.
And could you go back to the couple
This one?
Yeah, this one.
This is the question.
Right, yeah,
Okay,
that
go.
was the question.
So we are having a 2% miss rate for iCache and 4% miss rate for Dcache, right? And a miss penalty, every time we have a penalty, we have to pay 100 cycles. Because we didn't find something, we have to go down one level in memory hierarchy, so it's going to take us a time, right? And the base CPI was 2. And load and store are taking 36% of the overall instructions that we were running, okay? So for this, we can compute each of the portion of these two. And what else I wanted? Yeah. And finally, we can compute one version a CPU with a stall and the other version a CPU with perfect cache, and we can be divided together.
So in the total number of instructions is 100 in this case.
Yeah.
So 100 instructions will be fetched in the iCache.
Yeah.
36% of these 100 instructions will go with the
Yes. So a very good question by your colleague. Do you know why we are using 36 only here, right? Because only 36% of the instructions are load and write, load and store, okay? They're involving data, okay? That's why you have to, when you have 4% miss rate for your Dcache, you have to multiply these two and the 100, okay?
And the total miss will be the miss in the iCache plus the miss in the
Yeah, that's right. Okay, so there is another metric we can use for cache, for accessing access time. We call it AMAT, or average access time, right? Average memory access time. And on a very high level, it's normally a hit time plus your miss time. So whatever miss time you had, you're going to add it right next to it. So either you have a hit or you have a miss, okay? So that's why you have a hit time plus miss time. So how are you going to compute your miss time? Your miss time is miss rate multiply miss penalty, okay? And assume you had only one level of cache. If you had like 2 levels of cache, your miss would be miss of first level, L1, multiply the miss of the L2 level, right? So this miss could have been in multiple layers, because either way you're going to have a hit or a miss. And a miss in L1 could be going down, another miss in L2 and going down towards memory. So this could be expanded to multiple levels. And for each of those levels, you have to pay a penalty of its own, right? So the question here is, you have a CPU that with a clock of 1 nanosecond, the hit time is 1 cycle, and the miss penalty is 20 cycles. So every time we have a miss, we have to pay 20 cycles as miss penalty, okay? And the instruction cache miss rate is 5%. So how are we going to compute the average memory access time? So it's just a matter of having the hit time plus miss rate and miss penalty, okay? So average memory access time, although the hit was 1 cycle, though we have some miss rates and the penalty is 20 cycles, so we have average memory access time is going to get to 2 cycles per instructions because of the miss rate we have, okay? Is it clear? Was that clear? No? Why not? Okay, so think about it this way. You're looking for executing an instruction using its address, okay? You either hit, which is good for you,
Yeah, I understand this part.
or you missed, okay? Which is bad for you.
Yeah.
So if you hit, it's just one cycle, which is very good. However, 5% of the time you're missing, and for each of those misses you have to pay a penalty. So overall, if you want to make the average, so you're gonna have to weigh it out, right? So you have to weigh the times you are missing by the miss penalty you're paying for that.
20 cycles is a total amount of misses, right? And this is
Instruction iCache miss rate at 5%?
for the 20 cycles, is it
Oh.
total?
No, it's miss penalty. So the time you're spending to come one level lower from L1 to L2 or from L1 to memory and fetch the data and bring it back up. So that's the penalty you're spending,
Okay.
right?
Why is there a 1 there? 1 plus. Where does the 1 come from?
So that one is your hit time. Hit time was one cycle, right?
Okay, and why does it say 2 cycles per instruction when it's a time? Like saying cycles per instruction is more of a frequency than a time.
Where are you referring to?
The last line. Does that
Oh, so this is, so if you weigh it out, if you want to weigh it back, so now the average memory access time is 2 nanoseconds.
Yeah.
Our CPU time was 1 nanosecond,
Oh,
so now it's going to be a double of that, right? Okay.
Oh,
Yep.
question. Why? So how come we're not considering the decache misread in this question?
So it was a very high level, yeah, question.
So is iCache to retrieve data from memory? And would you consider decache to load?
No, Dcache is for data.
So is iCache to retrieve them?
It's to retrieve the instruction of that, yeah.
And decache would be
The data itself,
oh,
right? That's why we have iCache and Dcache. So here, that was an example of that. So this one was fetching the data, the other one was fetching the instruction.
Oh,
But depending on the type of instruction, one is going to get, so like for instance, for here, for load and store, Dcache is, dependent on the number of, overall instructions. So like in this case, we had 36% of the instructions containing load and store, so they are playing with Dcache. For the all of them are iCache is involved as well. So, okay, where are we? So in general, when CPU performance increased, the importance of not having a miss penalty becomes more apparent. So decreasing base CPI would be a great proportion of time spent on memory stalls, but not all the time. And then because of this, so whatever we've been talking about up to now was a direct map cache, which is not a perfect way to design a cache. So next lecture we're going to talk about associative cache, which they themselves has their own different classes. Either are fully associative or n-way set associative. And that's the bulk of the lecture on Monday. All right? Any questions? Okay, have a good night, guys.